The global industrial base relies on an extreme geographic duopoly for refined boron. Turkey's state-owned Eti Maden and Rio Tinto's operations in California control 72.0% of global refined supply. This concentration leaves advanced manufacturing highly exposed to localized disruptions. Eti Maden alone holds 62.0% of the world's estimated 1.3 billion metric tons of reserves. Rio Tinto controls 15.0% of reserves and 22.0% of production. No synthetic alternative to boron exists, making these two nodes single points of failure. The rapid scaling of clean energy is transforming boron from a traditional chemical into a critical transition mineral. Borosilicate glass for solar panels is the largest volume driver. Demand in this sector is projected to double to 1,750 kilotons by 2028. Simultaneously, high-strength permanent magnets for electric vehicles represent the fastest-growing segment. These magnets require boron to prevent thermal demagnetization in traction motors. This application is expanding at 12.8% annually. Total global demand is projected to reach 3,600 kilotons by 2028. This trajectory will outstrip planned capacity expansions by 350 kilotons. The structural deficit threatens to stall both solar and automotive supply chains. This structural deficit has permanently elevated the price floor for refined boron. Spot prices for refined boric acid rose from $750 per metric ton in 2015 to a peak of $1,450 in 2022. This surge was driven by a market deficit that emerged in 2019. The global balance shifted from an 80 kiloton surplus to a deficit of 140 kilotons. The duopolistic supply structure cannot respond dynamically to surging industrial demand. Even with minor corrections, the deficit remains at 125 kilotons in 2024. Prices remain locked above $1,400 per ton. This elevates downstream manufacturing costs for both advanced glass and permanent magnets. This concentration mirrors the 19th century global reliance on Chilean sodium nitrates for fertilizers and explosives. That bottleneck was only broken by the invention of the synthetic Haber-Bosch process. Today, no synthetic alternative to boron exists, leaving the energy transition bound to two geographic nodes.